Okay, let's dive into this. Welcome to the Explainer. Today we're tackling some grade 8 geometry. Specifically, we are focusing on those foundational right triangle trigonometric ratios, sine, cosine, and tangent. And look, we're not just going to sit here and mindlessly memorize formulas like a bunch of math zombies, right? No way! We're going to actually understand them as dynamic relationships that come directly from our core geometry standards on similarity and right triangles. So let's kick things off with what seems like a simple question, but it's actually kind of tricky. If I just point to a side of a right triangle, can you confidently tell me its name? Like, is it the opposite side? Is it the adjacent side? Well, it's a trick question. The real answer is it completely depends on where you are standing. In trigonometry, we like to call this the power of perspective, and honestly, it is the absolute key to unlocking literally everything we're going to talk about today. Now, what's really interesting about this slide is that it completely shatters a super common misconception. You know, people often think the opposite and adjacent sides of a triangle are these fixed structural walls, kind of like the floor or the ceiling of your bedroom. They just are what they are. But look closely. When we mark angle A as our reference point, side X is way across the triangle. It's the opposite side. But if we metaphorically walk over and stand at angle B, suddenly side X is right next to us. It becomes the adjacent side. The physical triangle itself didn't change size, it didn't change shape. Only our marked acute angle did. The labels completely swap just based on your perspective. All right, so with that strict rule of perspective in our back pocket, let's officially meet our first trigonometric ratio, sine. Sine is simply defined as the ratio of the length of the side opposite your marked acute angle to the length of the hypotenuse. And notice how we explicitly tether this ratio to the marked angle. You can't just find the sine of a right triangle in general. That doesn't make any sense. You have to find the sine of a very specific marked angle within it. Like I said, it's all about where you plant your feet. Next up on the roster is cosine. Now this is the ratio of the length of the side adjacent to the marked acute angle to the length of the hypotenuse. Again, it is all about that marked reference angle. But, I want you to notice something absolutely crucial here. While the opposite and adjacent sides swap around depending on your perspective, the hypotenuse, that is your structural anchor. It's the longest side, it sits directly across from the 90-degree right angle, and it is the only side that never ever changes its name, no matter which acute angle you're looking from. It's the one thing you can always, for sure, count on staying put. And finally, we have tangent. Tangent is the ratio of the length of the side opposite, the marked acute angle, to the length of the side adjacent to it. Now, what makes tangent uniquely interesting compared to the other two is that it doesn't use the hypotenuse at all. None. It relies entirely on the two legs of the right triangle. And because of that, keeping our perspective firmly locked on our marked acute angle is more important than ever. We have to be absolutely sure we don't mix up those two legs. Let's move to our next concept and see how this builds into solving actual, real-world math problems. Think about calculating the height of a flagpole using indirect measurement. To pull this off without getting completely lost in the weeds, we always follow 3 essential steps. Step 1. Mark your acute reference angle. Just circle it, draw a star next to it, whatever. Just mark it clearly. Step 2. From that marked angle, label your given sides as opposite, adjacent, or hypotenuse. And step 3, look at the information you have, look at the information you need, and just choose the trigonometric ratio that perfectly fits that exact combination. Let's actually put this into practice. I want you to literally pause this explainer for a second and try this out. Imagine you're trying to find that flagpole's height. You know your exact distance from the bottom of the pole, which we'll call the adjacent side, based on where you're standing on the ground. And you also know the angle of elevation looking up at the top of the pole. So, which trigonometric ratio, sine, cosine, or tangent, do you use to find the height, which is our opposite side? Go ahead, pause the explainer, think it through, and come right back. All right, welcome back. Great job taking a moment to work that out. So, the crucial point is how we align our knowns and unknowns. Our marked angle is the angle of elevation from the ground, right? Our known side is the distance to the pole, which is adjacent to us. And our unknown side is the height of the pole, which is opposite to us. So we need a ratio that connects opposite and adjacent. Looking back at our definitions, tangent is the only correct choice for this specific setup. You'd basically just set up an equation using tangent to solve for that missing height. Let's try one more quick challenge just to really lock this in. Imagine we scale right up to the very top of that flagpole. Okay, so if we move our perspective to the top of the pole, making the angle of depression looking down our brand new marked acute angle, are the opposite and adjacent sides still exactly the same as they were when we were standing on the ground? Pause the explainer one more time,
Apply the rule of perspective to this exact same physical triangle, and let's see what you get. And we're back. Well, if you said no, you're absolutely correct. And this brilliantly illustrates the core concept of trigonometric perspective one final time. The physical walls of our triangle, the heavy steel pole, the solid concrete ground, they obviously didn't physically move anywhere. But because we changed our reference angle to the top of the pole, the labels completely swapped. The ground, which was adjacent to us before, is now way down there, completely opposite to our new angle. It just goes to show that geometry relies entirely on your chosen reference angle. All right, let's do a quick, energetic recap to anchor all these concepts firmly in your mind. First, always remember that right triangle trigonometry relies heavily on the geometric principles of similarity and, most importantly, perspective. Second, and I really want this to stick with you guys, the opposite and adjacent sides are never fixed architectural features. They're entirely dependent on which acute angle you have marked. And finally, lock in those core ratios. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Now, before we wrap up this explainer, I want to leave you with a bit of a provocative transfer question to chew on. We've spent this entire time mastering right triangles on a flat plane, but how might this mathematical rule of perspective apply if we weren't just looking at flat, stationary triangles, but extending these angles continuously around a full 360-degree circle? Like, how does sine, cosine, and tangent behave when the triangle is actually spinning in a coordinate plane? It's a pretty wild thought. Think about that as you prep for your future high school math adventures. Keep questioning, keep learning, and thanks so much for diving into this with me today.